So in this short video, I'm going to be going over a number of different math methods that we're going to be using repeatedly throughout this class to solve problems. We're going to focus on calculus-based methods to solve three different types of problems. The first is a problem we're trying to maximize some function over a single variable. So for example, in one of the lectures, we're going to be trying to maximize a monopolist's profits by choosing the level of price which does so. Okay, so that's one example of a type of problem that we might try and solve in this class, but as I said, we're going to use these methods over and over and over again, and hopefully you'll be able to use these methods to solve other problems that we did not go over in this class. Another type of question we're going to look at is finding the maximum of a function of multiple variables. So it could be that you're trying to find the price and level of advertising, which together maximize a firm's profits. And the third type of problem we're going to look at is maximizing over multiple variables subject to a constraint. So for example, a consumer tries to maximize their utility by choosing how much of one good and how much of another good to buy, subject to the constraint that they can't spend more than their income or their savings or something like that. So these are the types of problems that we're going to be trying to solve, and we are going to be solving them for sort of two purposes. So if you think back to the first question of what level of price maximizes a firm profits, that might be a question which interests you if you are the manager of a monopoly firm and are trying to maximize your own profits. It's a little bit less obvious, but it also is something that regulators might care about. If a regulator is trying to predict the impact of some policy, they want to know what firms are going to do with the policy and without it. And we can predict what they're going to do by assuming that they're going to act optimally, that a firm is going to try and maximize its profits given whatever the regulations there are. And so if we know what their profit function is, we can predict their actions by finding the actions which maximize their profits. So even though we're not trying to necessarily maximize their profits, these tools can be useful for predicting what someone is going to do. So today we're going to go over maximizing and minimizing functions, sometimes subject to a constraint. We're going to be focusing on functions where z might be a function of x and y. So we're looking at z's and x and y's. In our class, we won't be looking at z's and x and y's. We'll be looking at things like p's and q's, prices and quantities and other things like that. But for today, we're just going to focus on the math. So to quickly review, we're going to be using functions. So in sort of a general form, you might have that some output variable that you're trying to maximize, like profits, or in some cases minimize, like costs. Some output variable y is equal to some function of x. So far I've just sort of written down some arbitrary function f of x. Now when we're trying to solve problems, we're going to use a particular functional form of x, or a particular actual function of x. So it could be, for example, in some problems that f of x is equal to, say, f of x is equal to 2x, or in another problem it might be that f of x is equal to, make this same, f of x is equal to 2x squared, or in another example it might be that f of x is equal to the natural log of x. Okay. So let's try plotting some arbitrary function. I'm going to illustrate this graphically. So here I'm going to have x on the horizontal axis. I'm going to have y, which is just equal to some function of x on the vertical axis. And let me draw this function. So you can see pretty clearly, if we were searching for a maximum, that maximum occurs about here. Now we can see that by looking at the graph. But suppose that you were given an equation. How would you find the value of x which maximizes that function? Well, the key concept that we're going to use is that the slope of a function must be 0 at a maximum. It has to be 0, otherwise it's not a maximum. Okay, so we can see that. Suppose that I sort of draw some other graph here, and I have some other function here, and you say, well, is this point here a maximum? Well, you can see that because the slope is not equal to 0, if you were to move a little bit to the left along this function, so we move sort of this direction along the function, you would reach a higher point. So this initial point could not possibly be a maximum. Okay, similarly, if you had a function which is increasing, where the slope is positive at this candidate solution, you would see that if you were to move further right along this function, sort of move along this direction, you would again reach a higher point. So that initial candidate solution could not have been a maximum. Okay, so now if you look back at this original function that I drew, if you move right or left along this function, you're not reaching a higher point. So this sort of candidate solution actually looks rather appealing. Okay, so what we're going to do when we're solving problems, or trying to find the maximum or the value of x which maximizes the function, we're going to find a value of x which sets the derivative equal to 0. Okay, that's sort of our candidate solution. If you're being careful, you would not be done at that point, because the slope being 0 is only a necessary condition for the input value to be the value which maximizes a function. And to show this, I like to draw a circle on this graph. Now you'll actually notice that the slope is 0 at the maximum, like we were hoping. We're trying to maximize a function. But you'll also notice that the slope is 0 at the minimum, which is the bottom of this circle. Okay, so that shows us that the slope being 0 does not guarantee that the candidate solution is a maximum. Rather, it's only what's called a necessary condition. It's necessary for the value of x to be maximizing a function, but it is not sufficient to guarantee that that value of x maximizes the function. Okay? So to show this point a little bit more clearly, I could draw 3 different functions. In this first function, which is globally concave, the candidate solution, where the slope is 0, is indeed the maximum, or the value of x which maximizes that function. In this second example, this point where the slope is equal to 0 minimizes the function. This function is globally convex, sort of U-shaped. Okay. And there's a third type of function which has what's called an inflection point, where the slope is equal to 0 at this point, but that point is neither the maximum or the minimum of that function. Okay. So this sort of illustrates how we might try and find out whether our candidate solution, where the slope is 0, is indeed a maximum, a minimum, or neither. The way that we would check that is we would take the derivative of the derivative. If the second derivative is negative for any possible value of the input variable x, then the point where the slope is 0 is a maximum. That is, if the second derivative is negative everywhere, then we have a function which is globally concave, and the point where the slope is equal to 0 is the maximum. If the second derivative, or the derivative of a function, is positive for any value of the input variable x, then we have a function which is globally convex, and the point where the slope is 0 is indeed the minimum of that function. And finally, if we have a function where the second derivative is sometimes positive, sometimes negative, depending on the value of x, then we may have a point, or our candidate solution might be an inflection point, which is neither a maximum nor a minimum of that function. Now, I've sort of glossed over this caveat to this point. We are assuming in this class that our functions are continuously differentiable. That means both continuous and differentiable. So if I were to sort of draw a function which violates that, we could see that it is indeed possible for the maximum of a function to occur where the derivative is not equal to 0. So let me first draw that for the case where the function is not continuous. There's sort of a jump at this value of x. You can see here that the maximum of this function occurs at this point here where the slope is not equal to 0. So these solution techniques may fail when our function is not continuous. And likewise, it might fail when the function is not differentiable. So here I've drawn a function where the maximum occurs right here, but the derivative as you approach this point from the left is different than the derivative as you approach this point from the right. So the derivative you're approaching from the right is different than the derivative as you're approaching from the left. This function is not differentiable at this point, and therefore our solution strategies might not work. Okay? So we're just basically going to assume that the functions are both continuous and differentiable so that we don't have these types of problems in this class. We're also going to largely ignore the fact that you have to take the second order condition to guarantee that what you found is a maximum or a minimum. We're just going to assume that the second derivative holds for whatever type of problem we're trying to solve. I do want to mention that in practice, you need to actually remember that you have to take the second derivative to guarantee that what you found is a global maximum or a global minimum. If you don't do that, that can be a very, very big mistake. Imagine that in your first job after you leave Brandeis, your boss asks you to find the price which maximizes your firm's profits. And you forget to take the second derivative, and there's a little mistake. You found the price where the slope is equal to 0, but it was globally convex. And so what you actually found is the price which minimizes the firm's profits. Your boss is not going to be happy, and you'll likely lose your job. So it's very important to remember that in practice. Okay, so the last thing that I want to do here is I want to do a couple practice derivatives, and then one example where we minimize a function. So after I write each of these, if you want to try it yourself, you can pause the video and try and calculate the derivative. So if you want to do that, pause it now. Okay, so the derivative of this first function, the derivative of f of x, which in this example is equal to 2x, with respect to x, in this case is just equal to 2. Let's try another function where f of x is equal to 2 times x squared. So again, if you want to try this yourself, you can pause the video now and then unpause it when you're ready. So the derivative of 2x squared with respect to x is equal to 4x. Now let's just do one more quick practice. So let's say the last function we're going to consider is equal to the natural log of x. So again, you could pause it if you want to try it yourself. Unpause it when you're done. So the derivative of the natural log of x with respect to x is simply equal to 1 over x. So again, if any of these derivative rules were something that you didn't remember because you haven't taken a math class for a while, I suggest that you review them. You should also be able to take the derivative of the exponent of x. So it could be like exponent of x, which you may remember as e raised to the power of x. Those two are the same thing. You should review those rules as well. And lastly, you should review the chain rule and the product rule. Those are two derivative rules, and be able to use those. Okay. So I'm going to erase that now. And the last thing I wanted to do in this lecture, or this short video, before we move on to the next video, is to try finding the minimum of a function. So let's say that y is equal to x minus ln of x, where the second part here is the specific function of x. Okay, so we're going to find the value of x which minimizes this function, which minimizes y. And the way we're going to do that is we're first going to take the derivative of this function, find the value which sets the value of x which sets the derivative equal to 0, and that's going to be our candidate solution. So let's take the derivative. We'll take the derivative of x minus the natural log of x with respect to x. And that's going to give us 1 minus 1 over x. Okay. And we want to set that derivative equal to 0. Now you could go through a couple steps to rearrange this to solve for x, or in this example here, might just be able to look at it. It's an easier example. You could see that when x is equal to 1, that the value of this part here, the derivative, is equal to 0. Okay. So our candidate solution is x is equal to 1. Now, for most problems in our class, you could stop here. We're going to assume that the second derivative holds. But for this problem, let's just make sure. Okay, so now what we want to do is we want to get the second derivative of this original function, or said another way, the derivative of the derivative. So let's take the derivative of this derivative. So the derivative of 1 minus 1 over x with respect to x. And the derivative of that is 1 over x squared, which you can see for any value of x you plug in is positive. The second derivative here is positive for any value of x that you would plug in. So we verified that this function is globally convex, and this candidate solution that we found right here is indeed the value of x which minimizes the function. Okay. So we'll stop there for this first lecture. In the next lecture, we're going to go over partial derivatives and solving for the maximum or minimum of a function of multiple variables.